And now we will discuss briefly about the conductometric sensor. That is a different kind of sensor which measure what? Conductometric sensor is an electrochemical sensor that measures the changes in electrical conductivity. Yeah, as I told you before, it it measures the electrical conductivity or resistance of a solution when an analyte interacts with the sensor. Widely used for chemical, biological, environmental sensing. So how does it work? It needs two electrodes set up, not three electrode. It needs only the working electrode and the reference electrode. And mainly these two electrodes usually made of platinum, gold, or carbon. And the electrical conductivity measurement, how will you measure it? An alternating current or small DC voltage is applied across the electrode, and then the conductance or resistance of the medium between the electrode is measured. And I showed you here the comparison between this conductometric and amperometric or potentiometric sensor. Here you can see it is measuring conductivity. It needs two electrode. It is ion based sensing mostly, and common application is water quality and biosensing. Yeah, so let's go to an example, right? So this one is the paper talking about the development of novel carbon dot is one kind of nanomaterial, the carbon dot. Novel carbon dot conductometric sensing for nitric oxide sensing. Okay, so it is kind of gas sensor. So these carbon dots obtained from a waste, they are calling it, they collect this carbon dot from the waste produced during the production of olive oil in Italy, and they are using it for nitrous and monoxide, or you can call it nitric oxide detection. So what is happening? The dynamic plot of this one you can see here. Normally we are getting how much we're getting the current. The dynamic response of this carbon dot sensor was verified by testing the sensor to a concentration of 1250 ppm nitric oxide at the operating temperature of 200 degrees Celsius, and the quantified response and recovery time amount to approximately 90 second and 200 second. So it is going back, it takes 90 second and is going down and is coming back, the recovery time. So the first one is the response time, and it come to the lower position, and then it is go back to its baseline. That is called the recovery time. It takes 200 second. Okay, and furthermore, the response, here we can see the responses. So the response of the sensor to different concentration of nitric oxide in the range from 125, starting from this one, 125 to 4000 ppm. Moreover, yeah, here, to verify the presence of a memory effect, they are doing it in the opposite direction. So they are running from 125 to 4000, and later they are starting from 4000 to go back to 125 ppm if the sensor can go back. So they measure the resistance, right? So the response of the sensor is reproducible. They can, from this one, you can see the graph, the block, and the black and the red dot for the response rate is really good. It is very reproducible over time, and also it is this graph is showing its good reproducibility at a fixed time, at a fixed temperature. It is showing reproducible effect. And in this one, it is showing that on the humidity, if the humidity is affecting this sensor, because mostly the gas sensor is mainly affected by humidity when you are going to measure the resistance. So that, and they are calling it that 1% of humidity has the same effect of less than 25 ppm of nitric oxide. So That means even if this preliminary result inferred that humidity do not influence remarkably the sensor performance. But I think the further investigation is necessary, of course. And let's go to the another conductometric sensor, which is the rapid and selective biomarker detection with conductometric sensor. Okay, so here it is just showing the what is happening here. They are measuring the biomarker. Okay, so there are two biomarkers they are basically measuring here. One is the cardiac inflammatory biomarker. It's called interleukin 6, or in short IL-6. And another biomarker is called a reactive protein. It's called CRP. So these two biomarkers they are detecting with this conductometric sensor. And this one figure A, it is showing just the structure, shows the cross section of the device platform, right? And then the optical image of this sensor, and here the yeah, it is actually the XPS. There is the X-ray photoelectron spectroscopy image, which shows the core level of oxide. And in the figure D, it is FTIR. That is the Fourier transform infrared spectrum. They are showing here the transmittance with the presence of zinc oxide and GPS. And GPS is one kind of molecule. It's called 3-glycidyl oxypropyl trimethoxysilane. Okay, so it is one kind of silane actually in this GPS. And here they're measuring the water contact angle. You can see here they're measuring the hydrophobicity of the zinc oxide surface. So in this sensor, they're using the zinc oxide and also using one kind of silane, that is the GPS. And with this zinc oxide and GPS, they are trying to measure these two biomarkers, IL-6 and CRP. And okay, from this figure, you can see here the GPS on zinc oxide device is stable for at least 6 months. Yeah, at ambient condition. This conclusion is derived based on they're calling it on time dependent measurement obtained for GPS on sealant using water contact angle. They're using this water contact angle here. And in this figure, they're showing the antibody immobilized device, the antigen binding onto antibody immobilized device. Yeah. So at first step, there is the sensor surface, and then a step one, this GPS salinization, that is the GPS, they're using it, and then the antibody immobilization. And then the step three is the antigen binding. So antigen means that the IL-6 and CRP, those are the antigen here. They are binding to the antibody. And here also antigen addition. Yeah, figure this one, the summary of the biomarker sensing technique proposed in this study. So after binding this, what is happening, we can see, yeah, in the next, in this figure, you can see here the IL-6 one, and then the fresh and reused one. So they are measuring the delta R as a percentage of difference, right? The difference of resistance as a conductometric sensor. So this in this one, both this IL-6 and CRP antibodies required an immobilization time of 5 minutes. At first, you can see here it takes 5 minutes at first, right? So at 5 minutes to produce the expected resistance changes, and then the optimum immobilization time for both this IL-6 and the CRP antigen to produce the expected changes in resistance is 5 minutes when the antibodies are immobilized. When this is optimized, it takes 5 minutes for both of them. And then these two figures, the reusability of the device is showing. And so this device can be reused to detect both IL-6 and CRP antigen accurately. Once the device was used to detect the antigen, the same device was immersed in DI water or millicube water overnight, and then they to remove the antibodies and antigen, and they use it again. And from the figure, you can see the fresh and reused are kind of showing the same kind of resistance changes. That means the sensor, after reusing, also they can use the sensor.